We start with unsupervised clustering. And for our example, we're going to use entries from the Dictionary of Canadian Biography, which is online and freely accessible. So we store our URL in a symbol, and each biography in the Dictionary of Biography has an ID, and I've hand-selected a handful of people for us to test this on. So here are the biography IDs. Now, when I wrote the code, they've changed the site a little bit, so the code as it was in the lesson originally didn't work. I had to change that slightly. So we clear the biography association, and now what this is doing is it's going to that web page, it's retrieving biographies for each of those men, and it's extracting the text, and it's going to store that in an association where the key is the person's name and the value is the text of their biography. That's what this does. And we can use view data to have a look at that when it's done evaluating, and we can see here's George Best. Key is his name in the biography as it's listed in the biography, and it points to a text that has his biography there. This is quite a long collection of biographies. Okay, and then if we just look at the keys, here are the people that we're going to be looking at. Now, the reason I chose these particular people was because I know something about their lives, and I know that they tend to fit into clusters. So I can look at them, and knowing something about their lives, I can cluster them by hand. And so let me just tell you a little bit about the people. If you want to know more, I've pulled summary plain text from Wikipedia data. So there's a pair of father and son explorers, a pair of Italian men, the Cabots. So those are two of the people. There is an English explorer named Martin Frobisher and a crew member on his expedition and a chronicler of his voyages, so those two fellows go together. There are some French explorers of the Mississippi River. They form a nice natural grouping. And there are some Jesuit missionaries who lived and died in New France, and so they form a grouping together. And finally, there is a fellow who doesn't immediately fit into the other groups, but he was an intendant of New France, and so he has some similarities with the other men. So we're going to store each of these Wikipedia summaries in another association. So now we have two associations. One of them has the Dictionary of Canadian biographies for each of those men, and the other has their Wikipedia summary biographies for each of the same men. So now we can compare the results of clustering on two different but related data sets. Okay, so Mathematica has a lot of tools that do cluster analysis and unsupervised clustering. There's a command called find clusters. We're just going to map frame across it so we can see the clusters more easily. So on the Wikipedia association, it puts Frobisher, Lassalle, Jogues, and Talon separately, and then it has a single cluster for the other men. And if we do this for the biographies, we get a cluster of the men with Lassalle and Talon separate. So in both cases, the unsupervised clustering algorithm has decided that these two biographies, Talon and Lassalle, are different enough from the others that they don't belong in the same group. It finds more clusters with Wikipedia association than it does with the biography association. Now, another thing that we can do is we can use hierarchical clustering, and there's two versions of this. One is called dendrogram, and you can tell it what kind of features you want to use, and I'm saying in both cases use TF-IDF. The dendrogram looks like this, and the way that we read this is we say if we start with all of them in a group, the first person to split off, the one that's most dissimilar to the rest, is George Best. The next person to split off is Frobisher. Then there's a branch that includes the Cabots, and a branch that includes the rest of the people. That's how we read that dendrogram. In clustering tree form, it looks like this. Best splits off first, then Frobisher. Here are the Cabots, and then here are the others down here. Another way to define the similarity or dissimilarity of texts than TF-IDF is what's called compression distance. And the way that compression distance works is quite easy to understand on an intuitive level. And that is, I'm just going to read this to you. If we use Cx to say this is how long x is going to be when we compress it, then a good compressor, if you give it 2 copies of x, should give you the same results as if you give it just a single copy of x. Since it's perfectly redundant, a good compressor should be able to squeeze out all that redundancy. If you have 2 completely different files, let's call them x and y, then the size of the compressed version where you stick them together should be the size of the compressed version of one plus the size of the compressed version of the other. So in one case, if it's the exact same file, we should be able to compress out all the redundancy. In the other case, since there is no redundancy, the compressed version of those 2 files concatenated together is the same size as if you just compress them first and then add together the 2 file lengths. Now the most interesting cases lie somewhere between completely redundant and completely different. And this gives us the idea of what's called the normalized compression distance. So I have a small function here to implement that using actual compression on these texts. And now we can try it out. So here we want to measure the distance of 2 strings that are identical. That gives us a distance of 0. That's good, that's what we want. If the 2 let me do the third one first. If the 2 are completely different, that gives me a distance that is a number here. And if there's some overlap, there are some x's in the second one and some y's. If there's some overlap, this number should be smaller than this number and larger than that one. So this compression distance gives us a way of measuring similarity or dissimilarity of texts by compressing them and testing the lengths of the compressed versions. So we can actually use this distance function. We can actually hand it off to clustering tree and dendrogram and see what results it gives us. So here's the clustering tree. And in this case, Talon gets separated out first, and then Frobisher, 2 of the Jesuits, the Cabots fit together in their own little branch over here, and the rest of the men are clustered in here. If we do the dendrogram, we see these are both, the first one was with the Wikipedia Association, and this is a dendrogram with the Biography Association. The length of the things here suggests a certain kind of, like the fact that this is all crammed together over on the left-hand side, all of the divisions is not great in terms of trying to figure out what's going on there. Hang on a sec. I think I've got this wrong. This was, the first 2 were supposed to be, the first 2 were supposed to be the Wikipedia Association, so let's change this to Wikipedia Association. There we go. Okay. Slightly better, but still kind of crammed together a bit. It does put the Cabots in a separate branch here and branch Talon off first and then Frobisher. If we do the same thing now with the Biography Associations, on clustering tree, we can see it in this layout. Now, we can also change the layout, so this doesn't have to look like a tree, for example. This is the exact same results, except for I've laid them out differently. So this figure is actually equivalent to this figure. It's worth knowing that how something is visualized often has an effect on how we think about it, even if the data are actually the same.